Okay, this is my second attempt to make this video about alternating series so that it has some volume. Alternating series in section 8.6. Let me turn it this way. So an alternating series has signs in between the terms that alternate from minus to plus or plus to minus. It doesn't matter which one. They're all called alternating series if every other sign is opposite. For the alternating series, we need these sums to hone in on a particular value. So for instance, if I look at my terms, my first term might be A1 right here, so that's the first partial sum. Then when I add A1 with A2, well, if A1's positive, A2 is negative, so it might take the second partial sum here. If A3 is positive, but A3 is bigger than A1, then my sum might jump up to here, but we're going to require that the sums bounce back and forth in here. The only way that the sums will bounce back and forth and eventually approach a fixed sum, or the sum of the series, is if the subsequent terms get small as you go down the line. That's what this says. The next term is smaller than the previous term, and not just get small, they have to eventually go to 0. So we're going to do two things to check if an alternating series converges. We're going to see if the general term, the non-alternating part, goes to 0, and if the AKs form a decreasing sequence of numbers. So here's a first example. This first one starts off, I've got a k plus 1 power, so when k is 1, I get a positive 2 as the power, so I get a positive sign, 1 over 1. Then when k is 2, I get 1 over 2, 1 over 3, and so forth. And this, for even numbers, k plus 1 will be odd, so every other term is going to be negative. This is called the alternating harmonic series. And if I do the two steps of this thing, of the alternating series test, I take the first step, make sure that the non-alternating term goes to 0 as k goes to infinity, and this one clearly does. Then I have to show that it's decreasing. So I take my AK plus 1 term, and I compare it to my AK term, and I need it to be smaller. My AK plus 1 term in this example is 1 over k plus 1, and that is clearly smaller than 1 over k because 1 over k plus 1 is bigger than k, so the reciprocal has it that 1 over k plus 1 is smaller than k. So it did the two steps of the alternating series test, so this series converges. By the alternating series test. Okay. The next series, we'll do the alternating series test on it. First, we check if the kth term goes to 0. And since it's bottom heavy, the limit does go to 0. In this one, it's hard to determine if it's decreasing by comparing AK plus 1 to the AK term. So in this one, I'm going to show it's decreasing by showing that the derivative is negative. So let's take the derivative with respect to k. Let's get a k out of that. The derivative with respect to k of the non-alternating part. We take the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And when I multiply that out, I get 8k squared minus 6 minus 16k squared all over 4k squared minus 3 squared. So I get a negative 8k squared minus 6 over 4k squared minus 3 squared. A common factor on top would be 2. I'm going to pull out a negative 2. So that leaves me 4k squared plus 3 is the second factor. And since these two guys are added and k is squared, I know that stuff is positive. I know the denominator is positive. And then take those positive numbers and multiply it by negative 2, and I have that my derivative is negative. So that means it's decreasing. So our conclusion is, by the alternating series test, this series converges. Okay. All right, so here again, this makes it an alternating series. We do the 2 steps of the alternating series test. We take the limit as k goes to infinity, and I get the exponent goes to 0, but e to the 0 is 1, and that's not 0, so this series does not converge. This series diverges. So just like in the test for divergence, you need the kth term, the non-alternating part, to go to 0. Otherwise, the series diverges. Every single alternating p-series are going to converge. Every single one of them. The first one we did had p as 1, the alternating harmonic series. 1 over k to the 4th, 1 over the square root of k with the alternating part, those are all going to be convergent because every one of those, 1 over k to a power, is going to go to 0, and they're all going to be decreasing terms. 1 over k plus 1 to a power is smaller than 1 over k plus 1. 1 over k plus 1 to a power is smaller than 1 over k to a power. So it is decreasing, and we know the limit goes to 0. So every single alternating, harmonic, or alternating p-series in the world will converge. A neat thing about alternating series is that we can see how close we can get to the actual sum. There is a theorem in calculus, an advanced calculus, that I won't prove here, that says if you know your series, your alternating series converges, and you add up, say, the first 5 terms, then I know that that sum is within whatever the term I leave off. The 6th term, however big that is how close I am to the sum. So it says if you have a sum S, and you just add up the first n of them, the distance between those, no, one might be bigger than the other, so let's put it in absolute value bars, that is numerically less than the term that you leave off, where Sn is A1 plus A2 all the way out to An. So it's whatever term that would have been out here that makes up the upper bound on the area. This is only true for alternating series. It's not true for series in general, but it's true for alternating series. So in the next example, I've got an alternating p-series. P is 5. Every alternating p-series converges, so I know it converges. I want to estimate the sum by taking the sum of the first 4 terms, and I want to measure how accurate this is. So I wrote out the first 4 terms. When k is 1, negative 1 squared over 1 to the 5th. Here's k is 2, k is 3, k is 4. Then I cranked them out, got out my calculator, and I got this number here, 0.971888664. Now, how close that is to the actual sum we claim is no more than A5, where A5 is, let's see, did the first 4 terms, A5, I wrote down, this should be a 5 to the 5th. Right, if I put a 5 in for each k, I get negative 1 to the 6 over 5 to the 5th. I better check that number on my calculator. Let me find a calculator. Let's figure out what 1 over 5 to the 5th is. Might have to correct that. Let me see. 1 over 5 to the 5th. Here we go. 1 divided by 5 raised to the 5th. There's 3 zeros and a 3 2. 3 zeros and a 3 2. So I don't have 4 decimal place accuracy. I have accuracy to 3 decimal places. There's got 3 zeros. So the next term I would only add 0.00032 to it. So that's where this little theorem is handy. You can get whatever accuracy you want, right? In fact, how many terms are necessary to get within 3 decimal places? Well, I got 3 decimal places accuracy because I got 3 places right there. So I don't know what I'm doing here. I have no idea. I don't know where these numbers came from. I don't know how this even pertains to that. Okay, so here's with 3 terms. With 3 terms, it says I don't have 3 decimal place accuracy. With 3 terms, I'm adding up the first 3 terms, and it should be no bigger than the 4th one. But the 4th term is 1 over 4 to the 5th, and that's where I got this 1024. The reciprocal of 1024 is 0.0009, which would affect the 3rd decimal place because it rounds up into there. So you can't add 3 terms to get 3 decimal place accuracy. You'll need the 4 terms. In general, if we want to know how many places are, so here I put the a plus first term in there for 3 decimal place accuracy, and then we just solve this inequality for n. But I found it by brute force. Now we've got the difference between absolute convergence and conditional convergence. A series converges absolutely, or is said to be absolutely convergent, if the corresponding series of absolute values is convergent. A series that converges but does not converge an absolute value is said to be conditionally convergent. So absolute convergence is the strongest convergence. If a series converges absolutely, then it automatically converges conditionally. But to show something converges absolutely, let's take a look at the 2 examples that I have for you here. So first, let's look at this example. Let's take that example in absolute value. What that absolute value does to this thing is it takes away the alternating part. That's a convergent geometric series, because R is a half. Since it converged in absolute value, it is absolutely convergent. But our alternating P series, if I look at the second one, -1 to the k plus 1 to 1 over k, put that in absolute value, we get the 1 over k, the harmonic series. This is a divergent P series. Okay, so it's not absolutely convergent. But we did show that the alternating harmonic series is convergent by the alternating series test. That was our very first example we did with alternating series. So the next theorem says what I said a minute ago. If you know that a series converges in absolute value, then the series converges with the absolute value taken off. The converse is not true. If the series does not converge in absolute value, it doesn't tell us anything about whether the series without absolute value bars converges. You've got to run some sort of test on it, and it's usually the alternating series test. So it's possible that you're going to have a series that's absolutely convergent and therefore conditionally convergent. It's possible that you'll have a series that's not absolutely convergent, but it is conditionally convergent. And thirdly, it's possible that you're going to have a series that's just plumb divergent. It doesn't converge in absolute value, and it does not converge as an alternating series. Here's an example, the sum of the sine of k over k squared. It's not an alternating series, but it's not a positive term series. If I look at the series in absolute value, well, the k squared's already positive. So really the absolute value just takes all the sine numbers and spits out positive numbers. And so if I did a comparison there, I can pick a bk series where the numerator is 1 and the denominator is k squared, because I know that a sine of a number is never bigger than 1. And in this example, I have that the absolute value, the sine of k, is less than or equal to 1. And so if I divide both sides by k squared, I have that my bk's are bigger. And notice that my bk's are a p-series, so it's p is 2, 2 is bigger than 1, it's a convergent p-series. So in this example, the series that I'm testing is smaller than a convergent series. And anything that's smaller than convergent is convergent by the direct comparison test. So I tested this in absolute value, got that it was convergent, therefore this series is absolutely convergent. Okay. Now we need some help in testing things for absolute convergence, and one of the things that we have is a generalized ratio test. If we do run the ratio test but run it in absolute value, if you get a limit smaller than 1, then you're done. You say this series converges absolutely. If you get a limit that's bigger than 1, then it's not absolutely convergent, so you check for conditional convergence using the alternating series test. If the limit is equal to 1, then you have to just look at what the series looks like in absolute value, like I did in the example with the sine of k over k squared. So I'm going to show you how this ratio test works for this example here. I'm going to look at the limit as k goes to infinity of the ak plus 1 term divided by the ak term, all in absolute value, and I'm going to set that, I got to figure out what that is, so let me take that away. And so in this example, well, this will look like the limit as k goes to infinity. There's my absolute value bars, -3, k plus 1. Remember, to get the ak plus 1 term, we just start replacing each k by k plus 1. Then we're going to divide by ak, which gives us the flip and multiplied version over here. Okay, so I wrote this as k plus 1 plus 1. That's k plus 2, duh. Let's now rewrite everything so I can see what cancels. Let's write this as -3 to the k times -3 to the 1. This is k plus 2. Remember that k plus 1 factorial means k plus 1 times k factorial. Now I've got this stuff over here. I've got a k factorial, a -3 to the k, and a k plus 1. Now that I got it all spread out there, we can knock out the like terms from top to bottom. Boom, that one's gone. K factorial's gone. And let's rewrite what we got. I've got the absolute value of -3. That's just going to be a 3. Then I've got a k plus 2 up here. And then a pair of k plus 1's multiplied downstairs. I don't need the absolute value bars because now everything's positive. As k goes to infinity, notice that the degree on the bottom is bigger than the degree on the top. So we have a bottom-heavy fraction. Our limit is 0. 0 is smaller than 1. So the generalized ratio test says that our series is absolutely convergent. And we're done. Think about how hard that would have been to test with the alternating series test to show that the limit goes to 0 and is decreasing. Very difficult. So this ratio test showing me that it's absolutely convergent really saved my hiney on that one. Okay, here's something that we're going to be doing a lot in the latter part of the chapter. We've got something here that is a function of x, and it's called a power series. I've got coefficients generated by the 2 to the k over k factorial as k goes from 1 to infinity, and then those are multiplied by increasing higher powers of x. When we encounter something like this, our interest is what values of x can I use to make this power series converge? So what we're going to do is set up this generalized ratio test in terms of that function of x, force it to converge, and solve for x. So I'm going to go back here. I'm going to solve this for x. The limit as k goes to infinity of my ak plus 1 over ak, and I want it to be smaller than 1. So in this example, my k plus first term is going to look like 2 to the k plus 1, x to the k plus 1 over k plus 1 factorial. Let's get the bars here. Divide by ak, so that'll give me a k factorial here, a 2 to the k here, and an x to the k here. And we're forcing it to converge. We'll put that little step in there where we can better identify what's going to cancel. Right, this is 2 to the k times 2 to the 1, x to the k times x to the 1. K plus 1 factorial is going to be k plus 1 times k factorial. Copy the other guy down and say it's smaller than 1. Okay, let's change to red and knock out the common factors. X to the k goes out, k factorial goes out. This x doesn't have a k on it, so I'm going to factor it out in front of the limit. It's still in absolute value bars. Here it is. But now my limit is going to be on all the stuff that's left. And what's left is a 2, that's it, and a k plus 1 on the bottom. Now just look at the limit. This limit right here, k is going to infinity and k appears on the bottom. So that limit is 0. So this statement says that I've got to take some x, multiply it by 0, and it's smaller than 1. Well, multiplying by 0 is going to make the left-hand side 0 no matter what x is. So this holds for all x. That means it converges for all x. Okay, you're going to see some examples where this will only converge for a handful of x's, but this one converges for all x. We'll come back to those types of problems later in this chapter. Okay, so here I'm ending this section on a very cool fact that I'm not going to prove just show you. If a series is absolutely convergent, then we know there's some sum out there. And for the absolutely convergent series, you can rearrange these terms in any way you want, and they'll still add to the same number. But if you have something that's only conditionally convergent, and not absolutely convergent, it's possible to rearrange the terms and come up with a different sum. Or you might even rearrange the terms and not even get a convergent series at all. So I showed you in this particular series the conditionally convergent alternating p series. If you just add them straight across, we've proved that it was conditionally convergent. We didn't prove that they do add the natural log of 2. But if I say swap the place between the 1/3 and the 1/4, keep the sign on the 1/4, just swap the places, use a little commutative property of addition. Swap the places with the 1/6 and then keep everything else going like that. I can make that sum, or we can make that sum add up to 1/2 of the natural log of 2. If we rearrange some more terms, the way the third example has it, we can make that sum add up to 1. So that can be shown with a computer program. You can add them up and swap them around and get different sums. But I think that's pretty cool. And we're going to use the fact that if you've got stuff that's absolutely convergent, you can do some stuff to it, like rearrange the terms. You can also do some calculus to it when terms involve functions of x. So let's upload this one and see if this taped the sound to it, and I'm sorry that the first one didn't work.